Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is the Maestro Fuzz-Tone FZ1 effects pedal as used to great effect by Keith Richards on the Rolling Stones song Satisfaction. And this is the schematic to one of many such versions of that pedal. I'm not sure if this particular schematic is the one used on Satisfaction or not. If you know for sure, one way or another, please leave a comment below. Anyway, this particular version of the FZ1 consists of 3 transistor stages. Now, these stages are using PNP transistors instead of NPNs as we've generally been looking at in this class. But to draw the schematic as if we would typically draw NPN circuits, namely having the emitter at the bottom, they actually put the negative power supply at the top. As an aside, I love this note. If the unit should ever need servicing, take it to a reliable radio man. The electrical diagram below should be shown to the repairman to assist him in servicing the unit. So this is from an era where a lot of the equipment you bought both came with schematics, and it was expected that competent technicians could repair things. Very different nowadays. Anyway, let's take a look at this. There's some bypass switching here that lets you either bypass the effect or use the effect. And let's see, the guitar signal is coming in from the left. There's this 100K input resistor here. And if you look at the way the thing is biased, it is a little strange because we're used to seeing another resistor here at the base, but we don't. You can still analyze this using the techniques that we've derived. Anyway, notice that each stage is capacitively coupled, and that means we can consider the bias for each stage separately. In this lecture, I'll look at a direct coupled example that's more difficult to analyze in terms of the biasing. But looking at the individual stages, notice that the first stage is an emitter follower. It's a common collector stage. So this first stage is acting as a buffer. The next 2 stages are emitter followers that are providing gain, and each of those is inverting, so the total structure is non-inverting. And let's see what else is interesting happening here. Oh, notice that the bias resistor connecting the base to ground for the second stage involves a potentiometer hooked as a variable resistor. And this is called a TAC. So this lets the user adjust the biasing. Now, we've been doing linear analysis in this class. Of course, the whole point of a fuzz pedal is that you're driving it to operate into a nonlinear mode of operation, and that's how you get the cool, weird distortion. But starting out with a linear analysis gives you an initial insight on how the circuit is working. So in this lecture, I'm going to take a look at a similar circuit. It only has 1 common emitter stage at the end instead of 2, and it's also directly coupled instead of capacitively coupled, and you'll see this makes the biasing a lot more complicated. Now, in the last lecture, we looked at a common emitter stage followed by a common collector stage. So in this lecture, all we're doing is swapping the order of those amplifier types, but as we'll see, this leads to some complications. So, as in the last lecture, we'll first look at the DC bias circuit, and then we'll do a small signal analysis. So, when looking at the DC bias circuit, we open up all of the caps, and we're left with this stuff over here. So, in computing the bias, we need to consider both of the transistors here and the currents associated with both of the transistors. So, let's first talk about the bias equation for Q1. So this is something we developed in a previous lecture, and it's expressed in terms of Thevenin equivalent circuit seen looking out of the base and looking out of the emitter, expressed in terms of Thevenin equivalent voltages and Thevenin equivalent resistances. So looking out of the base, we can compute the Thevenin equivalent voltage using 2 voltage dividers and superposition. Remember, we're imagining that we're cutting the line here. And this is the same kind of analysis that we've done in several lectures now. All right, so in terms of looking at the resistance out of the base, that's just going to be R1 in parallel with R2 after we imagine zeroing out these sources. Now we need to think about the Thevenin equivalent looking out of the emitter. And now this is a lot more complicated than what we had in the previous lecture. And again, we imagine that we're cutting the line here. We can imagine that we're under the influence of 2 sources. One is our power supply, but the other is the current that's flowing into the base, which I'll treat here as an independent source. And this always feels weird to me, but if we buy Marshall Leach's argument about superposition with dependent sources, this is a legitimate way to think about it, as long as you include everything before you actually try to solve for the circuit variables. All right, so using superposition on these two sources, if I start with V minus, well, I can imagine zeroing out this source here, the current flowing into the base, and then there's no current flowing here because I'm computing a Thevenin equivalent, so I imagine cutting the line here. So there's no current flowing, so there's no voltage being lost. So the influence of V minus on that Thevenin equivalent voltage is, well, it's just V minus. All right, so what about the current flowing into the base? Well, using superposition, I would zero out this V minus source. And again, we've cut the line here, so there's no current flowing here. The voltage that's developed by this current flowing across this resistor by Ohm's law is just the current IB2 times the resistance RE1. And I know I need to put a minus sign here because the arrow shows that current is being pulled out of the node. And before we go further, let me write IB2 as IC2 over beta 2. As far as computing the Thevenin equivalent resistance goes, remember when I compute that Thevenin equivalent resistance looking out, I zero the sources. So that corresponds to putting a ground here at V minus, and it corresponds to opening up my current source here. So I just see RE1. As far as the biasing goes, you don't need the Thevenin equivalent circuit seen looking out of the collector, but it is convenient to have it if you want to make sure that Q1 is operating in the active mode. And that Thevenin equivalent circuit just has a Thevenin equivalent voltage of V+, and a Thevenin equivalent resistance of RC1. So nothing too difficult there. All right, so now let's take a look at Q2. Okay, so for the bias equation for Q2, we're going to need the Thevenin equivalent circuit seen looking out of the base, and the Thevenin equivalent circuit seen looking out of the emitter. And the equivalent looking out of the base is now pretty complicated. It's not like the easy voltage division of R1 and R2 we had previously. We see that there's really two sources influencing the Thevenin voltage seen at the base here. One is this power supply V minus, but there's also the current coming out of the emitter here. And I'll treat this as if it's an independent source when thinking about this Thevenin equivalent circuit. All right, so by superposition, let me first focus on V minus. If I'm focusing on V minus, then I open up this current source here. And so there's no current flowing here because computing a Thevenin equivalent, I cut the line here. So there's no voltage lost. And my influence on the Thevenin equivalent voltage is just V minus. All right, so what about the current source? Well, I would zero out this voltage source. And again, I'm cutting the line here. So the voltage that we see here would just result from this current flowing through RE1. So that's given by Ohm's law. And the thing that's a little different here than what we've seen before is I do see a plus here because this arrow indicates that we're pushing current into the node, which is going to raise the Thevenin equivalent voltage. And before I go further, let me re-express this emitter current in terms of the collector current by dividing by alpha 1. All right, so when I compute the Thevenin equivalent resistance, I zero out the sources. So I open up that current source and I essentially ground V minus here. So all I'm going to see is this resistance RE1 to ground. All right, so what about looking out of the emitter? Well, that's pretty easy. We just have Thevenin equivalent voltage V minus and Thevenin equivalent resistance RE2 for looking out of the emitter. Now, once again, you don't need the equivalent circuit looking out of the collector to compute the bias point, but if you want to make sure Q2 is acting in the active mode, it's handy to have, and that's just V plus for your voltage and RC2 for your resistance. So there you go. So let me take the various expressions we have here on this slide for Q1 and plug them into the appropriate places. And similarly, let me take the various expressions we have for Q2 here and plug them into the various places. And if I do that, we can wind up with a slide that looks like this, that has all of the expressions combined. To try to clean up the notation here, I've left VBB1 and RBB1 in these terms, and then you can plug them in appropriately here. All right, so the first thing to note is that these V minuses actually cancel. I left them in just to remind myself as to where various things came from. But once you've done that, notice that this expression for Q2 involves IC1, but the expression for Q1 involves IC2. So I can't just find IC1 and then compute IC2 or vice versa. I actually have a 2x2 set of equations here. I have 2 equations and 2 unknowns, and I have to solve them. And that's a big pain, and I don't really feel like doing that. Let's go to Marshall Leach's ECE3050 website. 3050 is an earlier number for what's now called 3400. And let's scroll down to his section that says Class Notes, and we'll click on the notes for BJT bias equation. And let's see, we want to check out not example 1, not example 2, or example 3, or example 4. We want to check out example 5. So that corresponds to what we're looking at now. And here he actually goes through the pain of solving the equations. So he arranges the equations like a matrix, and he computes the determinant, and he does the yada, yada, yada. Anyway, the main point of what I wanted to go through here was to essentially show how to get those equations to begin with. Now, if you wanted to make your life a lot easier, you could assume that the current flowing out of the emitter of Q1 is a lot bigger than the current flowing into the base of Q2, because if you did that, then you might be able to say, oh, we could just ignore this term here. And then you could say, oh, well, we could ignore this term here. And then you could solve for IC1 just from this first equation, and then take that result for IC1 and plug it in here. And that would be simpler. Anyway, however you want to compute those bias currents, let's suppose you computed the bias currents, and then you can plug those into your expressions to get the raw input and output impedances for the transistors, the raw emitter resistances of the transistors, and the raw transconductances of the transistors. And now we can use those parameters in our small signal analysis. So most textbooks would probably analyze this kind of cascaded amplifier structure by treating these two halves separately, computing the output impedance of the first half and computing the input impedance of the next half, and using a voltage division rule for the interface between them. Here, I'm going to use Marshall Leach's technique of just doing everything in terms of Thevenin equivalent circuits, where I can just kind of write down the answer. So for the small signal circuit, we're going to assume that all of these capacitors are operating as shorts. And later in the class, I'll show you a more detailed way of treating these capacitors that lets us consider their effect on the frequency response of the amplifier. The other thing that I've done here is I've taken the circuit looking out of the emitter here, this tangle of resistors, and replaced it with this Thevenin equivalent RTE2, which for this particular configuration of resistors is just a parallel combination, but you could put some other network of resistors down here and just tweak RTE2 accordingly. All right, so I want VO, the voltage at the output. Well, if I know the short circuit current looking into the collector for that Norton equivalent, I can get the voltage with just Ohm's law. So I would have RC2 in parallel with my external load RL that we're including here, in parallel with RIC2, which is the Norton equivalent resistance seen looking into the collector. And we put a minus sign here because the arrow is pointing, indicating that we're pulling current out of the node. So it's IC2. Well, I can compute that from the Thevenin equivalent voltage looking out of the base of Q2 by multiplying that voltage by big GM for our second transistor. And I'll review what the formulas are for the big G's and the little r ICs in a future slide. Okay, so I can express the Thevenin equivalent voltage looking out of the base of Q2 in terms of the Thevenin equivalent voltage leaking out of the base of Q1 by using the Thevenin equivalent circuit looking up into the emitter of Q1. So I'll have VTB1 times a voltage division formula, where I'm dividing the voltage over this emitter resistance RE1. And the other thing I have in the denominator here is RIE1, which is the Thevenin equivalent resistance seen looking up into the emitter. All right, so what is VTB1? Well, I can get that from VS with just a voltage division rule, because I'll have this R1 and R2 parallel combination that I'm dividing VS over. So I have R1 in parallel with R2 in the numerator, and then I have RS plus R1 in parallel with R2 in the denominator. And we've seen this term a billion times now. Well, maybe not a billion. That's an exaggeration, but we've seen it a lot. So if you have those Norton and Thevenin equivalent circuits in your head, you can just write down a Mason flow graph like this right away. And I should apologize to anyone who's just joining us who stumbled across this video. I'm assuming that people have seen some of the previous videos where I established these Thevenin and Norton equivalent circuits, and I use them on some simpler amplifier examples where I spell out what I'm doing in more detail. Now, to compute this big GM and these RIE and RIC terms, we're going to need some other quantities, like the Thevenin equivalent resistance seen looking out of the base, which once I short this independent source here is just these three resistances in parallel. The Thevenin equivalent resistance looking out of the base of Q2, which is just going to be this RE1 in parallel with RIE2, which is the Thevenin equivalent resistance seen looking up into the emitter of Q1. And RIE1 can be expressed in terms of two different formulas. And notice RIE1 needs RTB1, so you can compute that and plug that in here. And later we might also need RIE2, depending on which formulas we're using. And for that, you can take this RTB2 and plug it into here. All right, so for big GM, you have the choice of 5 different formulas, depending on what is the most convenient. And for RIC, we have the choice of 2 formulas. I've written these here in a generic way. You would want to put 1s here on everything, or you would want to put 2s here on everything in order to get the expression for a particular transistor. So there's a lot of algebra here, but it really is just algebra. All you're doing is adding and potentially subtracting and multiplying and dividing numbers. There's no fancy calculus or differential equations, so don't be afraid. So to compute our small signal voltage gain, we can just take these various factors and multiply them together. And here I've taken the minus sign and put it out in front. Now we can consider some special cases. If the output resistance of the source feeding the circuit, this RS, is considered to be 0, well, then this goes away and this whole term goes to 1. So then this goes away. And now if I suppose that RO2 is infinite, then RIC2 is infinite. And now if I also suppose that RL was infinite, then all of this goes away. Then I'm just left with these terms. And so I have this term associated with my emitter follower stage. And then I have GM2 times RC2 associated with the common emitter stage. Now, it's not necessarily as simple as just considering what we had in the common collector lecture and then piling that onto what we had from the common emitter lecture, because there may be some weirdness hiding in these terms here, but you get the overall idea. All right, so what about the output impedance? We'll define that as the resistance seen looking into the junction of RC2 and the collector of Q2. Notice we're not considering RL in this calculation, since that's an external load and is not considered part of the amplifier. All right, so R out is just RC2 in parallel with RIC2, which is the Norton equivalent resistance seen looking into the collector here. What's RIC2? Well, we have 2 formulas for that. Here's one of them. Sorry, I had to split this up a little oddly in order to get it to fit on the slide. Anyway, in order to compute that, we need some other quantities, like RTB2, that's the resistance seen looking out of the base of Q2, and that's RE1 in parallel with RIE1, which is the resistance seen looking up into the emitter of Q1. And we also need RTE2, which we computed on a previous slide to be RE2 in parallel with R32. So you can go back and look at an earlier slide for that. And you can use whatever other configuration of resistors you need here. Now, to compute RTB2, we need RIE1, which is the Thevenin equivalent resistance seen looking up into Q1. And let's see, that's given in terms of the Thevenin equivalent resistance seen looking out of the base of Q1, which is just this parallel combination that we computed already. So if you actually substitute everything in, you would wind up with a really, really long expression. But if you just think through it step by step, it's a bunch of very small computations that you just sort of pile on top of each other. Note that through this series of dependencies, the output impedance does depend on the output impedance of the voltage source that's feeding the amplifier. That's an aspect of BJT-based amplifiers that I don't think is widely appreciated. Okay, so what about the input impedance? We're defining that as looking into this junction of R1 and R2 in the base of Q1. Notice that we are not including RS in the input impedance calculation since that's considered part of the voltage source driving the amplifier and not part of the amplifier itself. So that input impedance is just a parallel combination of R1 with R2 with RIB1, which is the resistance seen looking into the base of Q1. What is RIB1? Well, that's expressed in terms of the Thevenin equivalent resistance seen looking out of the emitter. So what's RTE1? Well, for that, we're going to have a parallel combination of RE1 with the Thevenin equivalent resistance seen looking into the base of Q2. That's RIB2. Okay, so it's RIB2. Well, that's expressed in terms of the Thevenin equivalent resistance seen looking out of the emitter of Q2, which here is that RTE2. And then we're finally done. Now, if I take this and plug it into here, and 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 do all of that symbolically, yes, you get a big, long, complicated looking expression. But if you think about it just one step at a time, take the numbers that you have and plug them in, it's really not too bad. Okay, let's think about some special cases. If you could approximate the raw output resistance of Q2 as being infinite, then our IC2 is also infinite, and our output impedance would just be defined by this resistor RC2, which we choose. And as far as the input impedance goes, let's assume that RE2 is reasonably big, and then that will get multiplied by 1 plus beta. Oh, I really should put a 2 on these. Sorry about that. There should be a beta 2 there and a beta 1 here. All right. Anyway, so then I would get some big number here, and when I take that big number and put it in parallel with RE1, our TE1 is mostly going to be defined by RE1. And then if I multiply that by this big number, beta 1 here, I erased my numbers. All right, then I would wind up with some big number here. And if this number here is big relative to R1 and R2, then I can pretty much define the input impedance by choosing R1 and R2, although there were a lot of ifs in my bit of hand waving there.